All right, so hello, welcome to the class. I got all your assignments in, which is great. Since I got it yesterday, I'll be looking at it. You should be getting some feedback by tomorrow. So let's just get started on the next topics. And if you have any questions, you can always, email me after the call anytime during the week. Or you can also feel free to interrupt me during the call as well as I talk. If you have any questions, we can get over it right away. Share my screen. All right, so this has been our kind of like a scribble board as I used to talk or the last class. So I'll make a separator in here. And we can get to the next one. So a few things that we're going to cover, just like an outline. We're going to touch upon linear regression a little bit. And then we're going to move into the next logical step in terms of modeling. From a historic standpoint, linear regression is a few hundred years old. So the next thing that happened was known as the generalized linear models. This is a family of models, so it has a lot of models like kind of popular models like logistic regression, which we're going to cover. Poisson regression, etc. Well, etc. And then based on the time, we might go on with some more additional kinds of generalized linear models. These are very popularly just called as PLMs. That's what I'm going to refer to. We're also going to basically cover some more probability stat concepts a little more from what we did last time. There's a concept of likelihood, maximum likelihood estimation. So I'm just leaving all these new terms at you, but we're going to cover these in a couple minutes from here. So we're going to do maximum likelihood estimation, and let's see how much we can cover in this hour, and then based on that we can expand this more. Oh, and one more thing we're going to do is linear regression with constraints that basically would cover lasso and elastic net. That should be a good goal for today. All right, so let's get it started. This is my scribble board. So last time we looked at linear regression. You've done some assignments, and I think they showed up to look reasonably well from a first look, but I'll be looking at them more carefully. So this is the linear equation for predicting or explaining a variable y, looking at the variable x based on a linear straight line. If you only had a bivariate variable, by bivariate I mean x, y, two variables. So one input, one output. Now, if you had multiple input variables and only one output variable, then the same equation could be written as, so this just means similar, as x beta plus epsilon. And by the way, you have an epsilon in here as well, which is just the error term that your line cannot explain anymore. The rest of the error that your line cannot explain with respect to y and x. So if you had multiple x's, so you would have multiple columns in your x data set. So instead of one variable, your y variable is still one variable. You have multiple variables here, and then your beta is just your coefficients, just like your m was one slope. Here you would have a plane. Instead of fitting a line, you're fitting a plane. So these are the coefficients of the plane. This is like standard matrix multiplication. So, and then the rest of it is the error. If you want to think through this a little bit, what's going to happen internally is if you have this multiple columns of x in your data set, and obviously you have rows of samples for each column as well. And then you're hitting it with a beta through a matrix multiplication. This is your beta. This is your x. the beta vector. So you would have beta 1, beta 2, beta 3 in here. If you had, you have 4 columns, so you have beta 4. 4 betas in here. So what's happening is this is the same as saying beta 1 just by matrix multiplication x1 plus beta 2 x2 plus so on. So that's how you want to explain your y. So it's basically combining your columns in a very specific proportion or ratio where beta 1 and beta 2 decide what is the combination of x1 plus the combination of x2 plus beta 3 times x3 plus beta 4 times x4 that's going to best explain the y. So this basically on your right-hand side is just like a equation of a line you had in here with univariate. If you have multivariate, it's an equation of a plane, and your plane is still linear, right? It's not a curve. It's not a surface that I'm bending. It's literally one plane. So this work and the solution for such a beta, which is all you need to fit this equation, was brought up by Gauss, and Gauss was literally like a teenager when he came up with this solution. It's called the least square solution. We discussed that your solution looks like the optimal solution for this problem is beta star equal to x transpose. In a case where you had multivariate, which also specializes to univariate case, x transpose times x inverse is a matrix inverse. X transpose times y. So you take your x and then you do this matrix multiplication with x and y's, then you get the optimal beta. This was the solution. It's known as the least square solution that Gauss came up with. And it's called the least square solution because you're literally doing the solution that you have here for beta star is solving this problem. It's the optimal solution for finding a beta that minimizes this problem. This is the optimal solution. It's a minimization problem. And this concept is called a norm, which is basically nothing but the sum of squares of these differences. So every time you get a difference for each particular row, so say if you had n rows in your data set, y and x, each row you get a difference of y, whatever your beta star is explaining, the model that you fit. And you call it the difference. And then if you square that difference, you have an error for that particular row. You're summing up the errors for each row that you're not able to explain. So if yi was 5 and your solution was 4.5, then your error, the difference is 5 minus 4.5 whole square. So you're summing up all those errors. So it's just like a sums of squares and you're trying to minimize it. So you want to have a least sum of squares. So it's called the least square solution that Gauss came up with. Now this is historic, still used very much today. Now what we're going to do is we're going to jump into the next thing that kind of logically happened historically and which is used today very popularly, the GLM, which is what I was mentioning in our outline. So this was the continue that we continued, so we're jumping into this phase now, generalized linear models. So however nice and beautiful the theory has been for fitting straight lines, if your data set was not really straight, say something like that, you would need something, so a straight line of any kind would not explain your data as good as it probably should. So maybe something very non-linear, so something that is not like a straight line would explain your data much better in terms of predictions, because you have other data points and you can use your model to predict it. This is your x, this is your y, as usual. So people are trying to think about what can we do from a non-linear model perspective. That was one thing. Number two, the regression models we're discussing, including linear regression, have 2 points of view. One is from a purely optimization standpoint. By optimization, we literally point to models that can be, whose solutions can be figured out as an optimization problem, like a maximization or a minimization. You're trying to optimize some loss function or an objective. So in linear regression, it was least squares. But there's another point of view you can look at it, which is a lot more detailed. It's called the statistical standpoint. So here, we've not discussed this for linear regression yet, but we're going to do it for linear regression GLM. So basically, the linear regression solution is kind of special in a way that if you solve for it using this optimization standpoint or from the statistical standpoint, the beta star that I showed you in the last slide or screen is going to be the same beta star. You're going to get the same answer, same formula. So here, for linear regression, these two end up converging very well. So let's jump into a little bit of the statistical standpoint before we get. So this is en route to our GLMs. So the y equal to x beta plus epsilon that you had in linear regression, it is assumed that epsilon are distributed normally. So are normally distributed with a mean and sigma square. Okay, so this is the variance of the distribution. A normal curve is the bell-shaped curve that we were talking about in the last class. So this is the mean of the curve. This is your standard deviation related stuff. So if you had a different choice of mean, you would have a different normal curve. So you want a normal curve at the center, so there's like the normal curve with the specific standard deviation. If you want a normal curve with a very large standard deviation, it would be something like that. So a normal curve with a very small standard deviation is something like that. This is the mean, this is the standard deviation. So a distribution just based on your choice of parameters can explain your data. And if your choice is very good, it explains the data very well in terms of how the data is being distributed from a probability or statistical standpoint. So it's assumed that the epsilon, the errors are normal. This is an assumption of the model. So it's not like the reality. It could be the reality many times, but in many cases it's not as well. So people assume this, and from a statistical standpoint, which we're going to touch in the next class, because we need to prop up some more of your probability and stat concepts, which you're going to do this class. But it's good to know that this assumption exists. So under this assumption, you have a different solution, but the solution matches with the same solution that you guys have seen before. Now, people were also thinking, hey, we want to fit nonlinear curves, but can we also come up, when people are thinking about GLMs, people are also thinking, can we come up with models where you don't have this kind of a strong assumption of normality on your errors, but you can have other distributional assumptions as well. So why not the errors be Poisson distributed if it's discrete data? Why not it be distributed by, say, a negative binomial or binomial, etc. So that was another thing people wanted to be able to do, and that's how GLMs came into place, generalized linear models. So the two GLMs we're covering, primarily more of the logistic regression that we're looking at. First is basically a GLM with respect to binomial distributional assumptions instead of normal distributional assumptions we had in standard linear regression. Poisson regression seems very self-explanatory to Poisson distributional assumptions. Okay. There's, based on your choice of distribution, you can have a different kind of a GLM. Now, let's get into the real nitty-gritty of the logistic regression first. So what a logistic regression does is this. So if you had a standard linear regression model like X beta, you're going to upgrade it a little more. So this was your standard stuff. It's a linear regression. But for logistic regression, people assume that the Logit function, so I will tell you what this function is, the Logit function of y is equal to x beta plus epsilon, which is also the same as saying, because you don't want to predict the Logit function applied on y. What you really want to do is, looking at your data, you want to have a model that predicts y itself. So the Logit, so you can always reshuffle this, like put in Logit inverse in here. So y is equal to, I will tell you what this Logit thing is. It's not a magic box or anything. You can open it up, but just assume it's a function for now. So you're going to have Logit inverse x beta plus epsilon. So that way you have a model to predict y's instead of predicting logit of y. And now the beauty is this function is no longer a linear function when you apply the Logit inverse in your data set. So initially you had a linear regression, but now when you apply this stuff over it, you're fitting a curve which is nonlinear. And logistic regression is very popular, although it's called classification. Its application is primarily in, although it's called regression, its application is primarily in classification problems. So it's a special case of regression in some ways. So if you had some data points, like say in here, some ones and some data points whose y, so I'm drawing y right now, or zeros. So basically you have a bunch of input data, and then I say for each xi, each record of input data that you have, say the input data was from emails, I would say this email was no spam, this email was spam, these were all the no spam emails, these were all the spam emails, but you have the input x for them based on what you have these y's, so whether they're spam or no spam. So you're trying to classify whether they're spam or no spam. So typically a shape of this curve that we drew here would look kind of nonlinear, something like this if it was a good fit. So it's no longer a straight line, because your straight line will never be able to explain this kind of data. Whatever, if you have a line here, but it's not able to classify. But in your logistic regression, this shape is usually called the sigmoid shape. This can vary however you want. It's going to fit based on how your data separation is. So that way, it's predicting primarily at any point whether it's more likely to be closer to a 0 or closer to a 1. So it's trying to classify is it email, spam, or no spam. So that's the nonlinear part. So it's much better than linear regression for a classification problem, which is not, because linear regression is not going to get you anywhere further. Now, from a standpoint of just understanding what this Logit function looks like, it basically looks like this. So y equal to e power, this is just your exponential, e power x beta, which you had anyway, by 1 plus e power x beta. Okay. By the way, Google has a very nice plotting capability. So if I were to say plot, most of the times it just works by just typing it in Google Chrome. Plot e power x. You know how the exponential curve looks like. There you go. This is the capability I'm talking about. So sometimes it may or may not work if I'm trying it live here. Let's see. That's another way to do it. And then if I say plot sigmoid, it may not work now. Okay, let's use that. So this is the sigmoid function we were talking about. That. Okay. So based on your choice of betas, this can move further. So right now, this is where it's classifying. If anything is above this value, it's more likely that it's becoming towards. If it is below, okay, yeah, if it's below -2, it's more likely to be no spam, and about 2, more of a spam, but there's some uncertainty here which is going on. Sometimes it can be very steep as well. We have more direct jump from one class to another. So these are like different kinds of logistic functions. Okay, so we're going to do that in terms of the prediction classification problem here. So we're going to have some coding assignments on a classification problem where you're going to fit a logistic regression. So I'll be sending you your assignment maybe by tonight or tomorrow, so that you have a full week to work at it. Remember, there was a statistical side of things as well in here, which basically, I'll tell you a little more about the assumptions, but we need to cover some more concepts before we get into more deeper aspects of it. So in a logistic regression model, so in linear regression, this was assumed to be normally distributed, but we distribute it. In a logistic regression, the epsilon, your errors, which you have here as well, are basically binomially distributed. So this is a binomial distribution, and if you heard of these things a little more before, you would have known, say, that the normal distribution is a continuous distribution. Your input x on which the distribution is defined is basically a continuous variable, like a real variable. But binomial, it's a discrete distribution. So is Poisson, which we're going to cover. So just if you see in this data, your output data points are discrete, the 0, 1, these kind of categorical in some ways. They're not continuous, like you're not covering the entire number line with numbers, you're only covering some discrete values. So that's why we use a discrete distribution to model this kind of phenomena. Now, a binomial distribution has two parameters. Every distribution has a mean and variance, so it has two parameters as well. So the mean and variance. And this also has another way of looking at it, which is binomial distribution has something known as a probability of a success when you're doing some discrete amount of trials. So if you're flipping your coin many times, the probability of success of getting ahead is the probability parameter that I'm talking about. So if you had that, you can always do 1 minus that to get the probability of failure. So the mean of the binomial distribution is n times p, where n is the number of trials and p is the probability of success. The standard deviation is np cubed. So Wikipedia, by the way, has great details of all parameters of every distribution. So I would highly recommend that anytime. There's a nice table on the right that it usually shows. So binomial of np. So n, because one must be the other one. This is the mean. It's np. The variance is np times q. So on and so. So this is the so based on your choice of p and n, you get a different kind of binomial. The question is, are we choosing the right p and n, the right parameters for the mean and variance, or the p basically, so that it explains your data the most, right? So if you had something like a coin toss, one kind of a binomial distribution would explain it better than some other problem like email spam. Sometimes it might not explain it at all because it may not look like a binomial. Maybe it's very skewed on the right side or left side, that kind of thing. So that problem of trying to estimate what parameters of a distribution fits your data the most is known as the statistical inference problem. There are graduate courses on that area. But one of the popular techniques that comes out of these is known as maximum likelihood estimation, which concepts everyone touch on a little bit. Yeah. So maximum likelihood estimation is a method of estimating the parameters of a statistical model given observations by finding the parameter values that maximize the likelihood of making the observations given the parameter. So this is what I'm talking about. So if you had data, which is your observations, and you want to know, and if you thought it was binomial, you still want to know, is it a binomial of p equal to 0.5, where the probability of success is 0.5, like in a coin toss, or is it a binomial of p equal to 0.7 in some other problem? You want to figure out that, and that is figured out using a technique. One of the popular techniques is called maximum likelihood estimation. They also call it MLE. That's the reason it's a little bit in here. So why are we going into this area? Because from a GLM standpoint, there's this kind of a view, but there's also a statistical view where I said your epsilon, the errors that you're not explaining, are binomially distributed. So, so what that means is the follows. Let me clear the screen right now. It means the same thing as saying y is also binomially distributed. That's how the properties transfer, because it's one single equation. So it's the same as saying the yi for each of your data point. So by the way, some notational thing you should be knowing. The symbol, like this tilde, is the symbol of distributed as. So yi is distributed as binomial of some n and p. Well, you don't need n here. N is not truly a parameter in some ways. A binomial of some p. So of some pi is the assumption we're taking. Just because if your error was distributed like that, and if you had an equation that also is dependent on the error, so then this is also a function of the error in some ways. So the left-hand side is also binomially distributed. Now, what this means is the follows. Let me give you a visual representation of your data set. So if I had some data like this, and then many here, for example. So what this is assuming is you want to fit a model where each of your yi's, this is your y-axis, x-axis, right, is binomially distributed with some particular pi. So you have distributed binomially, this point is some other kind of a binomial distribution. This is going to be very, and this is a very wide one. So that's the kind of assumption you're trying to make. This is the point around which it is centered, right? This is the point around which it is centered. So you're having a binomial distribution that you're assuming at each of your data point. Same case in linear regression as well. You know what? From a statistical standpoint, you have a Gaussian distribution. We've not touched the statistical aspects, right? We only looked at the more vanilla optimization aspects of linear regression and GLM. So under this assumption, what people do is you want to, so when people assume the follows, they want to predict the expected value of yi, because that's what you want to predict is equal to. So this is the statistical way of looking at your GLM problem. It's still the same equation, logit of x beta. Is what there's always an error, of course, that you're sometimes not explaining completely to the model. So it's still the same thing, but what you're really predicting is the expected value of y. So you want to figure out what is the mean of this distribution. So what is it that is on average most likely to be the value of yi for any given inputs of xi? So if I give you some email data for your x's, you want to figure out some beta that if you fit into that if you substitute in this function, this model in here, you would be most likely predicting on average what is yi most likely to be. Is it going to most likely, looking at this function, most likely going to be a spam email or a no spam email? So this is the statistical standpoint. Now, if you do that, and if you're assuming that yi is binomially distributed, expectation is basically, just to be clear, is nothing but the mean from a continuous standpoint. So if you had this 10 observations, if you want a mean, you sum them up and divide them by 10. This is the sample mean that we studied in high school. But if expected value is if you had a continuous random variable, for example, say like Gaussian, then it's the mean of a Gaussian random variable where instead of, so say here, this was a Gaussian with the mean in here. This is obtained, if you only had some sample data, how they obtain it is using an integral. Instead of summing up, you're doing an integration of each of your sample, xi, times the probability of that sample being observed. This is your expectation of x. This is the concept of mean for continuous variables instead of discrete variables. So that's the expectation. So this can be applied just using the sigma instead of the integral, just using the sigma, which is just the addition, in terms of the binomial case as well. So if you had a dice with 6 possible values, what is the, on average, what is the average value? If it's a fair dice, just like dice that you play in snakes and ladders or something. If it's a fair dice, and if you roll it 1,000 times, what number do you see on average the most? It's an interesting question. Is it 1? Is it 6? Are they all equal likely? But what is it that my average would be if I were to take an average of all those numbers that you get when you roll a dice by 1,000 times? So that can be mathematically written as, computed as follows. So you want to sum up sigma of xi times p of xi. So basically, xi would be 1. What is the probability of getting 1 out of 6 numbers? It's 1 by 6 because it's a fair die. Plus 2 times 1 by 6, plus so on. So this is the average you would get when you roll a dice. If you roll a dice 1,000 times and average all the entries that you got, it would exactly be equal to 1 times 1 by 6, plus 2 by 6, plus 3 by 6, plus 4 by 6, plus 5 by 6, plus 6 by 6. That's a fixed number. If you roll it 1,000,000 times, I will guarantee you that if you roll 1,000,000 times, write down each of the numbers that you got. So maybe 1, 1, 3, 5, 2, 6, whatever order you got them, write them down in an Excel sheet and sum up all the 1,000,000 numbers and take an average of that. I will guarantee to you that it will be very, very, very close to this, even with respect to all the decimal points to this number. So it's much easier to just compute this sum of 6 numbers than write down 1,000,000 dice entries, roll them 1,000,000 times, write them down in Excel and average them up. So that's the beauty in here. This is a closed form equation. So now we have a proper equation for this. Whenever you have an assumption of a binomial, you always have of any distribution, you always have an equation for this. So basically, you need to just figure out what this expected value is. Expected value is nothing but this pi that you want to figure out, because like I said, the mean of the binomial, well, n times pi, the mean of the binomial distribution is np. You know, n is 1,000. If you had 1,000 rows of data, 1,000 emails, you want to figure out the p exactly for each of these distributions, because you're fitting 1,000 distributions. You want to figure out the mean for each distribution. That will explain this model the best. Okay, so here, this is the first row of the email. You want to figure out, on average, is it more likely to be a 1 or a 0, a spam or a no spam? So the problem is of estimating this pi, which is the same as expected. So it's just going to give you expected value of yi, because expected value of yi is nothing but n times pi, as we saw in Wiki. Now, to be able to get this, you want to know, n, how many emails you have in your data set. So to be able to know that, like I said, there's a very big area of statistics called statistical inference, where the problem is to figure out from data what is the most likely parameter given a distribution that your data follows, which is this. And that can be done through this maximum likelihood estimation technique. So for now, I'll leave it there. Let's just call it a technique, because we're going to cover it in another call. The point of this call is to give you a big picture of how you go from linear regression to generalized linear models from a practical standpoint, and what are the mathematical or statistical concepts that have led to the development of this model and that are really needed to understand how this model works in great detail. But from a standpoint of the model, it's still good enough to know that you want to use, instead of x beta plus epsilon like in regression, you want to fit a nonlinear curve of this kind, which always has a shape like a sigmoid function, something like this or like this, depending on what fits your data the most. You want to figure out which shape fits it most and what that shape is, so that you can use it to predict and classify your data as whether it is spam or no spam, whether it's gender male or female, whether it's a criminal or not a criminal, just based on looking at your data. Whether the stock should be bought in the next moment or it should be sold, so that you increase your success rate from a revenue standpoint. These kind of classification questions. So that's it from a logistic regression standpoint. Now, Poisson regression. So from here, the detail reduces more. We had y equal to x. You take the linear regression in general, you put in some assumptions on the epsilon. So if you put a binomial assumption like we did, then you have the logistic regression model. So let's put in expected value of y is what you would use as your prediction of y, basically. To be even very specific, because we covered some conditional probability concepts, this should be, from a distribution standpoint, the way you're doing your model is this. What is the expected value? What is, on average, the expected value of y given your x? That. So x is given to you. You want to predict, on average, what do you estimate the average value of y to be for that particular x? That can be written as an equation of this form for linear regression, where epsilon is normally distributed. For binomial distribution, for a logistic regression, same thing. You're still predicting the same left-hand side. Right-hand side looks very similar, but your epsilon is binomial this time for logistic regression. Now, what about Poisson regression? Because that's the next technique we wanted to cover. So here, the assumption is kind of already in the question. So this is what you want to predict on the left-hand side using an equation of this kind on the right-hand side, but you're assuming that your epsilon is Poisson distributed, P-O-I-S. So Poisson, again, has a parameter. Every distribution has a parameter. Basically, the whole goal is about figuring out what these parameters should be for each yi that you're fitting in your data set. So again, in your data set, at each data point, you're fitting a Poisson distribution, some Poisson, another curve, another curve. Each has a different lambda I. So you want to figure out the lambda i's correctly for each curve so that you can predict the expected value of yi given xi. What that means is there's a very nice similarity now. There's a pattern that's building up in the math in here and the whole concepts in here, which is do nothing about the right-hand side. In binomial, you put in the Logit function before the right-hand side, which gives you a nonlinear curve, so it's fitting the data better. In a Poisson regression, you've put another curve. Instead of the Logit function, what you put is the exponential function. E power x beta is what you're trying to fit xi beta I plus epsilon will give you the expected value of, for that particular xi, you would get the expected value of yi given xi. So that is the reason these all are not just treated as individual techniques, but they form a family of techniques that is broadly called the generalized linear models. So you're taking a linear model, the linear regression, you're generalizing it in some ways because you're trying to make it a nonlinear model. So there are some distributional assumptions as well. So linear regression has so this is how a theory gets built, you know, and things come together. So the distributional assumption normal. Normal distribution is also called the Gaussian distribution because it was also another product of Gauss. He was the one who came up with this idea of a normal distribution, apart from doing the linear regression in general. It's also called Gaussian distribution assumption. So these all form the generalized linear model family. Now, the etc. If you choose a distributional assumption, you would get a different kind of a GML, generalized linear model, GLM. So there's a negative binomial distribution, for example, and you get a negative binomial regression, or a negative, let's call it negative, so on and so forth. So looking at this picture, all that is changing is some function you're applying before it. So if you were to generalize it a little bit, what you're doing is your input, your output based on some function that you take an inverse of, G inverse of x beta plus epsilon will give you your output yi. Now, for logistic regression, this is the Logit inverse. For Poisson, it's the exponential. For negative binomial, something else. So on and so forth. Now, there's also a nice reason for why this, if this was a Poisson, why this has to be exponential. Or if this was a binomial distribution, why this has to be the Logit inverse. Why not something else, you know? Why not logarithm in here? That kind of thing. The reason is as follows. Poisson distribution has one parameter that describes variance and the mean. It's called lambda parameter. Like I said, Wiki has a nice table for every distribution, like same format. Everyone uses this. So the mean is the lambda parameter. The variance is also the same parameter in here. Like in binomial, your mean was n times p. Here it was n times p times t. But the way Poisson works, it's like this. So lambda is what you care about here. This is how based on choice of lambda, you get a different kind of function that explains your distribution of the data. So there's a constraint on this lambda actually, that lambda can never be, you know, less than 0. That's how it is. So it has to be greater than 0, and it basically models count data. So things like how many overflow floods in 100 years. So that's a count that you're looking at. And for some choice of lambda, you'll explain it, the probability based on it. If you get the right lambda, you'll get the best probability. Or, you know, the count of how many goals in a match. It's always a count. So basically that, or like in a call center, the count of how many calls am I going to expect in this call center at 7 p.m. on a Sunday night versus 3 a.m. on a Monday night, etc. So you can model these kind of phenomena, count phenomena using Poisson distributions if you have the right lambda choice that you pick. And your lambda can never be less than or equal to 0. It has to be greater than or equal to 0. And it has to be positive, right? It cannot be negative, basically. And that's another reason why your G inverse in a Poisson regression case is exponential, because the exponential function is always a positive function. Even if I did e power x, where x is any number, I would get a positive answer. Even if I did e power minus x, I would get a positive answer, because that's equal to 1 by e power x, where e power x is positive. So there's no way you can feed in anything into this that will give you a negative answer if it is a positive function. So that's why it's ensuring, because you're trying to model the expected value of yi on your left-hand side, given xi, which is what you want to predict, right? On average, what distribution should it be, so that you know on average what yi would be. And since we assumed epsilon is Poisson, we also are directly assuming, because of that the yi is Poisson.
the yi is Poisson, and if you're trying to predict the mean value, which is going to be lambda I, because it's y, we just went to the Poisson distribution, and lambda I can never be negative. So you cannot put in whatever function you want in here where you might end up getting negative values. So then the whole thing collapses. The theory doesn't work. You will not be able to estimate the parameters using likelihood estimate. There's no longer Poisson that way. So instead of things to not collapse and you still have an answer, you're making sure you put something in here in terms of the inverse so that it is restricted to only give you a positive value. So whatever you feed in here, negative, positive, once you apply G inverse, which is exponential, you would end up getting a positive value. And a positive value can very well model the expected value of a Poisson distribution, which is your assumption. Okay. Now comes a nice question that everyone needs to kind of ponder about, right? It's not like a puzzle that I'm throwing at you. So if I give you, for a given x comma y, how do we know whether, so in a regression problems, right? For a given x comma y, how do we know whether linear regression or logistic reg or Poisson reg, etc., fits the data better and explains the yi well in the future. That's why. Well, in the future. What do you know? Because it's fancy models. So it's very easy. There are two ways to do it. One is you literally try everything. You try linear regression, you try logistic regression, try positive Poisson, negative animal, but whatever you want to try. If you try all of those, you would literally see which ones are predicting y better, because you always have a notion of error, right? In regression, it's your mean square error, like you did in linear regression. Same thing. You will, regardless of what this internal magic box is on the right-hand side and left-hand side, as long as you predict something that looks at y, x beta and tells you what the y is, x and that tells you what the y is, whatever your magic is in here, this whole thing, you can always see how different they are based on the mean square error. You can always measure y minus x beta and say, okay, I tried this. Here you'll have some function of x beta, right? Your function can restrict it to this being linear regression, or it could have been GLM, Poisson, GLM, logistic, etc., etc., etc. Now or in the future, maybe you learn 10 more techniques, whatever you try. You always have this error regardless of what you're doing. You're dumping X into the thing, Y into the thing, you get an answer out, you see how the error is. Whatever explains the data the best, you choose that model. Is that all it is? That's almost what it is. There's a little more to it, which what makes it a little different from just optimizing for the error. We're just being able to do machine learning. So these are things we would cover a little more later. But for now, this is the loss function or the objective function that you're trying to minimize. And based on that, you choose. So you basically try a few things and choose it. There's another way to do it, which is instead of looking at the optimization standpoint, you can do this optimization and then this basically statistical standpoint converge very well together. But what people do is they cannot just minimize the solution using an optimization standpoint once you're out of linear regression. For Poisson logistic, you have to do it to the statistical standpoint, which is you have to figure out these lambdas or the piece in binomial logistic regression case using the maximum likelihood estimation method. This is the only way to do it. And that requires some optimization as part of it later. So there you would optimize for it. So people come up with an objective function, which is changing now. So we discussed. So what is the objective is basically the question that is coming up with. Objective function that you want to, that you need to optimize. Choose the solution or even choose which technique is better. Is it the least squares? Yes, but there's a little more to it. Because the least squares, you cannot optimize this and get the solution. This is the thing we care about, but you don't get the solution directly from it. There's no way to do that. Then you have all these statistical assumptions. So the way people do it is using the maximum likelihood method. So the objective that is optimized for is the likelihood function. So we've not discussed this. This is what we're optimizing for. Then you get the solution. Once you have the solution, then you look at, you know what this function would look like. Then you can literally predict and see how the mean square error looks like. So obviously there is optimized for likelihood. is likely function. That is optimized for what? It's optimized for obtaining the solution to GLM models. GLMs is the likelihood function. Now, the objective, objective to measure, quantify the performance of your model is mean square error, which is what we looked at, this sum of squares of errors, like this stuff. So once you have the solution, which comes to the likelihood, then you can measure this, how far it is from your prediction. The mean square error for regression problems. And for classification, there are quite a few metrics you're going to cover in future classes. Because in classification, if you think about it, if I'm doing spam, no spam, there's not just one kind of error you can do. There's these many kinds of errors you could do. So basically, say the true value was 0 and the true was spam, and the true for some emails, and the true value was no spam, not spam for some emails, spam, not spam. And this was your predicted value of spam for some emails, and the number of emails that you predicted as 1. If you had 100 emails in total, so there's a lot of numbers that go in this table, this 2x2 table. So there would be some emails that you do. So let's make it easy for you. The 0 is say spam. This is not spam. That's the labeling. So this is again the spam label. This is the not spam label. So it's not one kind of error you make like in linear regression. You couldn't have a spam email. This is the truth. This is the truth direction. This is the predicted direction. This is what your model is thinking. There could be some emails that are spam that you do predict and classify with your model as spam. So whatever number goes here is great. You're saying these are spam emails to your model just by looking at the input data of the text of the email. But your model is not 100% right? My Gmail, if I open it today, I'm sure it has some spam in its spam box. So, and some Gmail is reasonably good, but maybe if I open some bad email server, then maybe I would have some spams coming into my email as well. So you could have some spam emails that are predicted as not spam. So this is a bad thing. This is false negative is what it is called, false negative. Because you're calling it not a positive, you're calling it a negative. So a positive is like a hit. You caught the thing as spam, the thing that missed out. So you ended up getting some spam in your email inbox itself. So those you have predicted as negative, but it's a false decision. So these are the false negatives. So you can have maybe 10 emails in your inbox over the last 3 months, which are false negatives. So that's like a bad prediction by the Gmail model or your model. And what else can happen? You can have a not spam email predicted as not spam, because you don't want a good email from your dad or from your professor ending up in your spam box or from your employer in the future, because then that's a bad thing. So this is a good thing. So here your not spam is here. It goes here, and 4 is being predicted as not spam. So that's one kind of thing. So that's the good thing. Like the not spam is predicted as classified as spam, that's a bad thing now. That's about the number of times that could happen in N3. So here, there's a beautiful not spam offer letter, but it ends up in your spam box because of the model of classifying as that email as being spam. Then it's a problem. So this is a false positive kind of an error. N3 is false positive. N2 is false negative. This is false positive. These are bad things. Now there are names for good things as well, the ones in your diagonal. Spam predicted correctly as spam. True positive. This is also true positive. True negative. Your choice of negative and positive is just can be changed. You can also call these as negatives and these as positive, or these as positive. But the diagonals are the true decisions. The off diagonals are the false decisions. So what you want to optimize for is you want to maximize these numbers, the true decisions, and minimize these numbers, the off-diagonal decisions. So as you see, it's not one single number that decides the performance of one classification model. Because in linear regression, it's just your sum of squares of difference of the errors, right? And you take an average of it. This is one number that can quantify the performance of the linear regression. But for evaluation metric or quantifying the performance of the classification model, there are 4 numbers that you need to look at carefully. And based on these, you can come up with newer metrics that depend on these 4 numbers. So that's the reason it's a separate topic for another class. But it's good to know what are we, optimizing our model on. So logistic regression does classification. So you need to go through this framework to say whether a logistic regression of this kind of parameters is better, or is there something else you need to, or was there some other classification model? Say there's a technique called neural networks that can do classification. Which one is better? Sometimes logistic regression does more better than neural networks. Sometimes neural networks does better than logistic regression. But how do you quantify it? You look at these 4 numbers of how it is classifying and misclassifying to decide the performance of your model. Okay, so this is what we covered this class. I think the lasso and elastic net should be covered in the next class. So let's stick to this in here for now. I think that's a good point to give a logical conclusion at this point. So I'll be sending you some assignments on fitting logistic regression and Poisson regression models. You'll have some data sets and some pointers to how to fit that to R. So at this point, I'd like to leave some time for any questions, any advice, anything you'd like to ask me. Is there anything of that kind, or we can just call it a day and have a good weekend? And you can always email me the questions. Any questions? All right. So, yep, I'm calling it a day. You have a good one.
Yep. So last time we worked on a data set, but we took the whole training data, fed it into the model, and predicted something. But do you think it's better to divide the data set into 2 different parts and use a part for training the model and test with an unknown data set so that you know what's happening?
Yeah, that's a great question. I do think it is better divided in 2 parts, and there are other designs in terms of how you can divide that data set as well. This is where there's 2 things here. One is, how do I fit a model or any given data set? Because even if you divide the data set into 2 parts, there is one part of the data you're feeding into the model, right? So the training X part, the training Y part, and then you're predicting on the test X and test Y. So
Yeah.
train X and train Y, now I have the smaller chunk of data set. How do I fit the model? That is what we're trying to learn right now till here. How do we fit the model? And then you bring up a very interesting point, which is, how do I evaluate the model once I deploy it in the future? Say,
Yeah.
office or in a university, you have some limited data. You split it or not, whatever it is, however you feed it into it, you know how to fit the model for a given amount of data. You get the model, then you deploy it in your company, and your company's decisions and money-making capabilities and customer service and everything is dependent on your model, and you left it in the wild, right? So you need to be able to some guarantee that it's performing well, because there you don't have a validation step. You're only getting the X into the model, and whatever your model is predicting, the company is believing it as possibly what the prediction for the Y is supposed to be. So there's a lot of designs on how to evaluate these setups very well, and that's why they call it machine learning at this standpoint instead of just calling it model fitting or something. We're going to cover these aspects actually. So definitely the way to do it. There's very interesting designs apart from this thing. So it's a good point that we're going to do that in a few classes later. Not right now.
Thank you.
Cool.
Yeah. Hi, Praneeth. This is Manideep.
Hey. Yep, go ahead.
I have a couple of questions. First thing, so for the last week assignment, I've done the linear regression for the data set.
Yes.
So, I understand. I don't understand some parts of the R statistics, the Harvard HTML file. But that needs a practice. I understand. But we are summarizing the model, right? So it gives me a lot of data.
Yes. Yes. So you're talking about once you fit the model, just so that I get your question correctly. You fit the model, then you're trying to summarize it in R, like
yes.
The model.
I'm trying to summarize it with R model. Yeah, I fit a data set into the model, and I'm summarizing it.
Yes.
So it says there are some keywords like coefficient, intercepts, all the columns, and f statistic, p value, etc. squared, and all.
Yes, yes. So very good you brought this up. This is very important, right? Once you fit the model, you should be able to understand and interpret it yourself.
Yeah.
So
So
what we
how
will
to,
do-
yeah, how to conclude this thing and what we are getting out of the summary. I understand what is coefficient, I understand what is intercept, but to put in the words, I'm not getting anything out of it.
Yeah, I mean, that's a good question. It's a good point. So what we're going to do is, I do believe this to be very important. So we're going to do, I'm going to take a screenshot of a standard summary that a linear regression produces on your data set or any data set. And then I'm going to go over each and every term in there and what it's explaining, right? There's so many numbers, so many terms and terminologies like that, like the F-tests and the p-values and all that. We're going to go over that. Some things I will put it aside because we're going to cover it in our syllabus. We have some chapter 7 or 8 each. We're going to cover the concepts of p-values and hypothesis tests and stuff. So those things I would say we're going to cover then. And that's the reason there is also 1 week that I put there that I've called it as revision in our syllabus file, but basically that is looking back at the models you learned in the first few weeks, and then you've done some assignments and learnings in the next few weeks, but those learnings in the next few weeks would also help you understand what you did in the first few weeks much better. So this is an example for that. So I think you're getting ready for that syllabus curve. Soon you'll soon get there. But there's always parts of your summary that are still, you can explain right now from what you learned till now. So that thing we will do as an exercise. Maybe in the next call, I will literally show you the screenshot in the beginning of the call for the first 5-10 minutes and tell you what this exact number is, what this terminology is, what it's pointing to from a practical standpoint. It's definitely worth that deserves a question that deserves a sitting and looking at it for a while. So we'll do that. Any other questions?
Yeah, I have one more concern. For all the class we had today, I understand in bits and pieces. I don't say I'm really good at everything you said today. So it all depends upon my next week work.
Right.
So while sending your assignment, like last week you did, you included few sources to get into from basics as well, because I really like that you are giving a source links and all to learn. So I will be needing today's classes source links if you have anything. Instead, I go with the Google various links and get different data. So if I have something from you, that would be like good for us.
Yep, I do have some really good source links, yes. I can do that. Let me share my, I don't know, so yeah, this is a question session, but if anyone's going out of time and have other things to do, you can always jump off the call. But let me share my screen for the next 2 minutes again. So one good link is PSU, the Penn State University stat, the GLM, for example. It will give you a nice course website, but it's not only about GLM. If you keep going back to the beginning of the course, there are other things it covers as well. So there's a few links in here, like the GLM. I'm going to share these things. So this is how it says how you have the GLM family. You have a link function, the Logit for logistic, and something else, Poisson, etc., etc. Or the inverse of the link, the function. Then we have log versus vector and anything. And then as you keep going, you will have more specific examples. It's a good site in general. People even use for interview preparation. Here he tells you how the model is looking like. We discussed this, before. There's an example which will give you, more of a feeling of how it fits in a real setup, etc. stuff. So I will share you some things of this kind. Also on your linear regression thing, let's do linear regression summary R. There's things I can, say for example that, right? So your linear regression output will look in this format. Is that correct?
Yes.
Yep. Yeah. So this is some other data, like random, right? I just picked something live here. So on Google Images. So basically, this thing, this is what you're feeding in. It's just repeating that. This is the data set. This is the model you're trying to use for X. This is the Y.
Yeah.
The residual is kind of easy as well. This is your mean square error. This is the median residual that you're using, that you have. Any questions on this? This is basically the subtraction of your out prediction minus the real Y and seeing how far your model is predicting the real y. And then there you're doing the square of that, and then here you're not doing the square. Let's have the negative here. It's just the residuals, the subtraction. So the median looks like 1.876, but in this particular example, for some other data set, there are residuals where for some particular x's, the worst error you have is like 1148 or 1425. This is even worse because it's a bigger number in absolute value. So it is 1425.753 numbers away from what the true prediction is supposed to be for a particular xi. And here it is much lesser, 1145. The true prediction. That kind of thing. So this is the residual part. Now the coefficients here, this is the betas, these estimates, which I'm sure you understand what this is referring to, is the betas. So is the beta that is hitting this variable, is the beta hitting this variable, so that's the model. The standard error t-value. So the standard error is basically your estimate always has some variability because you're assuming your data is coming from some distribution, right? So it's a phenomena, right? You have some x's and y's you're collecting from some real life phenomena. And it's not going to be exactly the same thing if you collect it after an hour or maybe after 6 days or 6 years. There's some variability. Same thing with respect to, say, to be specific as an example, the heights of children in class 4. It's not always going to be forever the same height that you have every year in class 4. Even within the same year, people are growing, kids are growing. Even within the same year, within the same batch, the heights might change a little bit. But as soon as the batch changes the next year, you have a different distribution of heights, So there's a variability similarly around everything, including your coefficient you're trying to predict. So if there is a very high variability, it's not a good thing. Like this thing is not a good thing for the intercept. It's okay. If it was for, say, so this is not good, especially for the UNEM variable, because the model believes that the beta 2 coefficient for UNEM is 4.5 power into 10 power 2, so 450.1. But it's not very confident about it. It says it's 450.1 plus or minus 118. So it could be 450 plus 118, 450 minus 118, or somewhere in that interval. It's not very tight, It's very, very variable. So that's not a good thing. That's what it's saying. It's saying about how much variability or confidence it has around this estimate it's making. Here it's much tighter. This is very sure that beta 3 is 4.065 to the power minus 0.01, which is 0.4065 is what this number is. It's very sure it is 0.4065 plus or minus 0.007, which is a very small number. So it's very tight about this, very confident about this. Same thing here. It's kind of reasonably tight. These are small numbers. This is horrible here. You cannot believe what the coefficient is supposed to do. Yeah. But the bad thing is, if this is horrible, in general, when you're summing up beta 1 times this variable plus beta 2 plus this plus beta 3 times this plus the intercept thing, your overall model is also varying just because of this bad guy. So it's always a good idea to, in these cases, for example, from an exploratory standpoint, this is a real thing you're doing, right? Your thinking is also going into what you're seeing in your results. It's not like you just give this to your boss this way. So what you need to think about it next step is, hey, how about me drop this variable because it's giving the model a hard time and see if the residuals don't change much, and if these two variables are explaining good enough, well and good. I have a model that is kind of tight that will not change every day when I deploy it, because there's an error around it in terms of being able to predict the true values. And so that's what this is saying about. Now the t-test, we're going to study these tests. This is called hypothesis testing, the area. There's books and volumes in this area, but we're going to study it from a practical standpoint in some of our follow-up weeks. It's in our syllabus that I've written down. But basically, this is testing for the follows. It wants to test the exact same thing that I said a minute ago. Is this variable worth dropping and not using in our model and still get good predictions? The same thing applies to the second variable, the h-grad or the inc variable. So this is basically testing what is the probability of not making an error if I were to drop this variable, which is the same as saying what is the chance that this estimate is equal to 0 and you're still good. Because if it is equal to 0, you're multiplying 0 times this data, and it's equal to saying you're dropping the variable. So basically, this is a test that will let you make that decision in the right way. And these two columns come from that test. So for now, how the inner workings are worth another class, or apart from other hypothesis tests we're going to discuss in that volume of discussion. But from an interpretation standpoint, if you have 3 stars in here, this is your legend. It says it's close to 0, which means these are highly significant. So it means that these are good variables. So it's basically rejecting the test. So let me be clear here now. You have this overall story I gave you, then we have this question of, am I supposed to drop this variable or not? Till that you should be understanding, right? So you need to answer that question very rigorously. So that's the problem you have at mind. Now, what this is telling us is the follows. It is doing a test of whether do I reject the hypothesis that this is equal to 0 or not equal to 0. If this is equal to 0, it means I'm going to drop the variable. If this is not equal to 0, you're rejecting the hypothesis and you're saying I'm going to keep the variable. So this is a test for, these stars will tell you the probability of rejection is significant or not. So it is rejecting the fact that this is supposed to be 0, which means although the error is high, it's still saying it is not worth dropping the variable. So it is saying it is highly significant. If it was somewhere here, if you had like a one single dot instead of star, then it is not very significant is what it means. So you basically just look at this from a practical standpoint without even understanding this at this point, and you can just say, hey, I have stars for all, so let's use all the variables. But if I have 3 stars and 2 stars for some, 1 star for some, then there's ones with very low, no star or low star, then it's better drop that variable, is what it's saying. That is a test that is happening here. This is the standard error of this residual, so not the coefficient, this is the variability around this residual, or the confidence around this residual that you're having. R squared is a different concept. It's the higher it is, the better. It is trying to measure the proportion of, it's like a proportion of what you're explaining and what you're not explaining. So this is very important. R squared linear regression. So I like the VT usually. Yeah, coefficient of determination. So, yep. So your error basically can always, so this is your error, right? Your mean square error. This is your prediction. Not this, sorry. Your mean square error is not written down here as a formula, but it's basically, here you don't have the average. You have like yi minus y predicted value. Y is the true value, y is the predicted value. That error can be decomposed into a sum of different kinds of errors. So it can be decomposed as what you're predicting here. This is your residual. This is what I'm looking at. So this is what you're predicting, plus your prediction times Fi is your prediction basically. Prediction times the average value of y's plus your true value from the average value. So basically there is a formula, there's a theory where you can literally break down this quantity, which is your yi. There's no prediction here yet. From the average of your yi, that variation can be written as the sum of your prediction from the average value and your prediction from each individual value. So the SS total is equal to SS reg plus SS residual. And R square, ideally you want to have SS residual by SS total to be as small as possible. Because your residual is your error. You want this to be as low as possible. So instead of looking at this number is like, if you see in this example, can take any kind of value. It's not in a fixed scale, right? And here you have these kind of range of values and some other problem, another range of values. So you cannot compare which is better than the other. Because it's not always between 0 and 1, or from 0 to 100. It's not like our GRE test. It's always from 0 to 340 or 0 to 1600. It's not a standardized scale. So R square is the same concept of how your error is on a standardized scale. Because this ratio, this is supposed to be as low as possible, and this is supposed to be as high as possible. So this is what it is. So this needs to cover this as closely as possible. So it measures, the lower this is, the higher the R square is, because then you are getting 1 minus a very small value, so the closer you are to 1. So that's the reason. The higher the R square, the better your model on a standardized scale. Whereas you can also take the same relation just by looking at the residuals, but you're not on a standardized scale. You don't get answers always between 0 and 100. You can get 15,000 as a residual. You can get 0.007 as a residual. Depends on the problem and the scale of values you have in your original yi's and xi's. So that is the component that this is referring to. R square and just R square, very similar concepts. F statistic, p-value, these things we should be covering later. P-value is quite a lengthy concept. So for now, what you get from this is you can analyze this, you can analyze these stars of which is important or not important. You can just look at R squared quickly and say it's closer to 1 or not. That's it. How the tests work is a separate class. Any other questions? All right, so so let's call it a day. I'll send you the assignments today or tomorrow. Let's stick to the same kind of a plan. You try to solve some of these assignments. We catch up next week. If you have questions in the middle, you can email me. If you have follow-up questions like today, we're going to cover them either during the or after the class tomorrow. Next week, based on what you're asking me. I'll also send you materials and links as you prefer. That's it. You have a good day, good weekend. Bye-bye.